Hey guys, I recently did a video taking an in-depth look into the ballast device used in the Motorola electrostatic TVs of the late 40s. I got a lot of great comments, some interesting topics were brought up, one of which is protection, what happens if some components fail. So we're going to talk about that in this video. I'm also going to include some things I left out of the original video because it just got to be so darn long, which would be the other type of ballast, the 303, which has a resistive element, and what was it used for. And I want to talk a little bit more about that Amperite glass ballast and how the current regulation effect works in it. Alright, so here is the circuit I recommended, which uses two diodes to drop down the voltage, the power going to the tubes. To recap a little bit, these are the pin numbers on the ballast. This resistive element is used for the B+ power supply, as is this one in the middle. The other two go to two tube filament strings that each have 300 milliamps going through them, which join up and go to the 600 milliamp CRT, the 7JP4. The original used purely resistive elements to reduce the power getting to the tubes. I recommended two other approaches, either using diodes or capacitors. But what happens if they fail? Yes, absolutely, they can fail. It's not the end of the world. It's not great, but it probably won't kill the tubes. So let's go through and do some math. Let's take the top branch. So with this short circuits, it's just gone. The power's getting right through it. We still have the CL90. We still have the 18 ohm resistor here. In typical operation, this is going to be 3, 5, 7 ohms, something like that. Let's just call it 5. Okay, so we will have 23 ohms of resistance here. How much current is going to be going down through this? Well, without doing some experimentation, we're going to have to estimate it. Assuming 125 volts coming in, and we have 300 milliamps down this, when the things are working right, this equivalent resistance is about 285 ohms. So if we factor that in and pretend this will stay fixed at 285 and we have 23 here and 125 at the input, what's that total current flow if the diode wasn't there? It's approaching 400 milliamps. Which, yes, is absolutely, it's 33% higher than 300. That's not good. If they both shorted out, we would have another 400, and the total here would be 800. Not ideal at all. But the tubes would probably survive. They would glow a bit brighter. The reason I say that this is making an assumption here, the tube filament resistance varies with temperature, which is a factor of how much current is going through it. The more current going through it, the hotter it gets, the more resistance it has, which will resist the flow of current going through it. I can't tell you without doing an experiment exactly what this would settle in at. It's going to be more than 300, might not be quite as high as 400, but it will be higher. No, it is not ideal. Probably the tubes can take it. Something you won't see on a spec sheet typically is what is the maximum, absolute maximum filament current. Sometimes they might say plus minus 10% from 300 milliamps, which would be 330 is the max, so yes, we are exceeding that. The one we're really concerned about is the picture tube. Picture tube filaments are more rugged. Not only is it rated at 600 versus 300, but you may have heard of brighteners. Those are transformers you can put on a weak picture tube filament to boost the power going into it, to run it harder to compensate for weak emissions. those will push them pretty hard. Picture tube filaments are they're more rugged than your typical picture tube. I'm not saying they're indestructible. 800 is by no means great, but if you put a brightener on it, it would certainly be more than 600. It might be 700 plus milliamps. What I'm getting at is your set is not instantly going to die. Yeah, it would be great if we could do something about it. It would be great if you noticed and you could turn the set off immediately. Similarly, if we had the capacitor version and the capacitor shorted out, it'd be a very similar situation. This side won't be affected quite as much, I don't think, because there's a larger resistance here, but there's also fewer tubes in the string, so it's probably roughly a similar effect. I think I got a comment from one or two of you, add a fuse. If you've ever spec'd out fuses, designed a power supply, experimented with fuses, you know it's not that simple. Might be thinking, oh, either before or after this we throw in a fuse symbol, for which is something like that. Better yet, probably put a fuse in either string, because this gets a little complicated to figure out what the appropriate current should be. So, okay, great, let's put a fuse in here and a fuse in here. What value fuse are you going to use? And what type of fuse you're going to use. I'll tell you where the problem comes in, and I'll show you some data to back that up in a minute from an actual data sheet. Fuses might not work like you think they do. Let's take a simpler example, say a 1 amp fuse. If you put 1 amp through a 1 amp fuse, it will blow. Eventually. It'll take a while. If you put 2 amps through a 1 amp fuse, it will blow, but not right away. There's actually a logarithmic relationship. A fuse is a piece of wire, typically. Similar to the resistive elements in the ballast as it was originally designed. And the wire will fail when it gets hot enough to burn through and the metal fails. That's not an instant thing, and it's not an exact thing where a 1 amp fuse and you put 1.00001 amps through it, it doesn't blow instantly. There's also some tolerance involved. And there's various types. There's slow blow, there's fast blow. Imagine if you had a perfect fuse and you put one in. It was a 300 milliamp fuse, and if you go to 301 it blows. That's going to be blowing all the time because you're going to get a surge current when you turn the set on. So we need a magical device that will allow a surge for a little while, a surge that's not too much, that will fail appropriately when we want it to. Those devices don't really exist. Now, one thing you can do that one of you, I believe, mentioned is put a magical device across this called a TVS diode. It's essentially back-to-back Zener diodes. I forget the exact symbol for, but it's something like that. That's tricky too. I did it in a video a while back. The way they work is they will start conducting when their breakdown voltage is exceeded. The tricky bit is, just like with a fuse, what value do you want to use? You might be thinking 6.3. Well, no, because we don't have exactly we have 6.3 volts RMS across the filament, but these devices work on peak voltages. And when we use a rectifier, we end up getting a complex waveform. So it's not so much the voltage across the filament we're trying to limit. We're trying to limit the amount of power going through it. And that's where things get more complicated. I can tell you this, if we just had a purely resistive and we had a sine wave across this, the sine wave across it is more than 6.3 volts. I think I ended up using TVS diodes that were 8.4 volts. is just like with the fuse, you don't want to be right on the edge. So say under normal operation, the peak-to-peak voltage is around 8, 8.2, 8.4. I forget exactly what it was. These devices have a margin, say they're plus minus 10%, and you don't want them to be conducting all the time. They'll get hot, they will fail. They can only take so much power, but you don't want to use over spec, otherwise they won't do their job and this will die first. What I'm getting at is if it was really easy to add a foolproof safety device to this circuit, I would have. Another topic came up with the capacitor version. Transients. Yes. The capacitor version, it's essentially a high-pass filter. We have a resistor in series with a capacitor. So if we have our nice sine wave, great, but you can get a spike. You'd mentioned somebody turning on a vacuum cleaner, or there's a lightning strike in the area, whatever. Yeah, you can get a transient spike and it'll go through this, go into your tube filaments. A few things about that. One, the filaments don't have internal resistance. They're going to somewhat absorb that spike, as will these resistors. Also, say there's 10 tubes or so in this filament string. Scattered throughout them, there are capacitors going to ground to take noise off of the filament line. I think they're 1500 picofarads, something like that. They will help absorb spikes. So I don't think that's really a concern. But if you are concerned about it, you can add a capacitor, 0.1 microfarad, 0.01 microfarad, use a safety cap, or a cap rated for across the line use. For that matter, put a cap across the line. One of these guys. An XY rated cap. Put that right across the AC line. That will absorb spikes. Or perhaps you've seen flavors like this. A Rifa cap, for those of you who work on vintage computer stuff. These guys that are prone to failure. But yes, put a modern equivalent of one of these across the AC line, and that would help out your voltage transient issue. Let's get back to talking about fuses. There's a nice graph I pulled up, courtesy of Bell Fuse. Across the top here we have different fuse ratings. 200 milliamp, 250 milliamp, 315 milliamp. That seems like a good fuse size choice, right? We want to have 300 milliamps going through normally. If it goes above that, we want the fuse to blow. So let's go with the 315. Okay, the axis vertically is time in seconds for the fuse to blow, and across the x-axis we have the current going through the fuse. Notice at the bottom they call something out here. Note that a 1 amp fuse will blow after 10,000 seconds with exactly 1 amp applied. Yeah, it's not that simple. A 1 amp fuse will blow with 1 amp after 10,000 seconds, which is a very long time. That's what I mentioned earlier about if you put a 300 milliamp fuse on it, it would blow eventually. Let's see, 10,000 seconds is 166 minutes. So about 3 hours after you're playing your set, it might stop working because the fuse finally failed. Okay, but they have a 315 and we want to fuse it so that at 300 it'll keep working. Okay. There, let's zoom in a bit. This is logarithmic. This is 0.1 amp going through the fuse, 0.2, 0.3. And here's our line for 315 milliamp. So it looks like if we have 0.3 amps, we're to the left of that line. So it should never blow, right? But we definitely want it to blow if a diode shorts. We might have somewhere around 400 milliamps going through it. Okay, where does that happen? Well, if we look down and follow that 400 milliamp line, it hits around here. If we go over, that's 2,000 seconds. 2,000 seconds is quite a while. That is 33 minutes. So if your diode blew and you had a 315 milliamp fuse in there, your set would keep running for approximately half an hour before the fuse failed. I don't think that's what you want if you're trying to save your picture tube from catastrophic failure. So a fuse is not going to do it. I hate to say it. A slow blow fuse would take even longer. Fuses are not exact devices. When they hit their rating or slightly above, they don't instantly blow. It follows a curve like this. Some of you that have worked with or designed power supplies may be familiar with a crowbar circuit. That is a circuit when a trip point is hit, either voltage or current immediately shuts things down. Problem is, generally those circuits are designed for pure DC power supplies. Here we have either AC or complex AC plus DC in the case of rectifiers. I don't know of a crowbar circuit that can accurately handle that. That wouldn't be very elaborate anyways. So remember, we're trying to keep something practical that somebody can make to restore one of these TVs. By all means, add a fuse in case something catastrophic fails, like there's a dead short somewhere on this side. Put a 2 amp fuse in there, fuse the whole set, absolutely. But as far as fusing the individual filament strings for 300 milliamps, such that if it goes a little bit over, it'll shut her down, I don't know of a practical way to do that. I almost forgot. Another topic that came up in the comments is that of the type of resistors I'm using. Whenever possible, I try to use fusible resistors, also known as fusistors. You may know them as these crusty old guys that were used back in the day to both limit inrush current, typically to a voltage doubler, as this is being used for, but also as a fuse. So if there's a problem, say a selenium rectifier shorts out, this would open up like a fuse. It took some hunting to find the specs on these, but it turns out this is rated for about 5 watts. Well, guess what? They still make them. This is the same thing. 5.6 ohm, 5 watt, fusible resistor. Turns out most metal oxide and metal film resistors made today have fusible characteristics. These brown ones made by Vishay, the PR01, 02, 03s you see me use so often, are all fusible. If you pull up their data sheet, there's a section on their fusing characteristics. And they're very similar to a conventional fuse, meaning that the more they exceed their rating, the faster they go open. So, in essence, I have fused these. I might have used a wire wound for the 7, but you can get 7 watt fusible resistors. It's a little bit harder to find, but the 3s, the 5s, those are easy to get. So, I have essentially also fused this. Again, by the time this opens up, it will take some minutes, maybe hours. Meanwhile, your tubes are cooking. So it's not ideal, but it is something. And certainly if there's a catastrophic failure, like a dead short somewhere, these will open up quickly. Let's talk about the other ballast type. This is something I didn't think existed until about a year ago when I scored it. This is the 17A470303 ballast. It's what Motorola used for all their versions up until the TS4J. I didn't know that Amperite ever made a glass ballast version of this. I set up a search on eBay over 15 years ago, hoping to get some of the metal versions. They may not still be good. At least I could hollow them out and replace them with one of these more modern circuits. But lo and behold, I got a hit on one. And yeah, Amperite made the glass version of this. Only one I have ever seen. Now what's the big deal about these? It looks like it works on exactly the same principle as the ones inside the metal tube, right? We have resistance wire It's separated by some mica. Okay, it's in this neat glass package, and maybe there's a vacuum inside so oxygen won't corrode it. But no, this is a current regulator. That's what they mean by automatic regulator on the box. This is filled with hydrogen gas. And the wire is a special alloy based on iron. Somebody somehow discovered that hydrogen, being such a small atom, gets absorbed into metal, and it affects the resistance of it. And the amount of gas that gets into the metal is dependent on the temperature of the metal. So they tinkered around and found the right gas pressure with the right alloy such that it's happiest with 300 milliamps going through it. Cools down, it absorbs more hydrogen, its resistance drops, lets more current go through, it heats up, boils off some gas, its resistance goes up, current drops down. That's why these are neat to find. Yeah, they get just as hot as the originals, but they're current regulators. That's a really neat thing, I think. Alright, so why are there two versions of ballast? Well, the 303 has an extra resistor. We talked about there being 4 resistive elements in it. This has 5. The extra one goes between pins 6 and 8. It's called E on the schematic. Where is it used? Down here. Hey, here's our 2 filament strings with our 105s. They join up, they go to the pitcher tube V15. What the heck is this? There's another tube in the string. V7. What is V7? It is a 6SQ7 that they're using just as an audio preamp before the final output. They don't use the 2 diode elements in it. Later designs dispensed with that. I think they use half of a 12SN7 up there. Okay, we're using a 6SQ7. Why do we need another resistor? Well, look how the resistor is connected. It's going right across the filament. Look up a 6SQ7. It's a 300 milliamp filament. Why don't we stick it up here with all the other 300 milliamp tubes? Well, if you add all these up, they've already been accounted for with the 2 ballast resistors. If you throw that tube up in here, you would need to lower this resistance. I suppose they could have shunted this with an external resistor, but they chose instead to shunt this tube with a resistor down here. We have 600 milliamps going through the CRT. This needs 300, so there's 300 that go through that resistor. If we do the math, 6.3 volts, 22 ohms, that's going to be in the ballpark of 300 milliamps. So that's what the extra resistor is for. And so they could cram an extra tube into the string without upsetting all this stuff up above it. It goes after the CRT, but it needs half the amount of power on the filament, so they threw in an external resistor shunt to handle it. Later sets don't use it. Eventually they phased out using this ballast tube and used a different one. I hope that covers everything. However, if any of you have some other thoughts on how we can add some practical protection to this ballast device, I would love to hear about it. For now, that's it. Thanks for watching.